Welcome to my talk on designing ecologically optimized vaccines. This talk will focus on developing vaccines against the Streptococcus pneumoniae bacteria, also known as pneumococcus. It is usually harmless in most adults, but in young children and in the elderly, it can invade the bloodstream, the brain or the lungs, causing meningitis, bacteremia, and pneumonia. This is called invasive pneumococcal disease. The World Health Organization estimates that pneumococcus kills 500,000 children under 5 years old, primarily in developing countries in Asia and Africa, each year. The pneumococcus bacteria is encapsulated by a polysaccharide capsule. And based on these different types of capsules, it can be categorized into roughly 100 different so-called serotypes. They have varying degrees of invasiveness and antibiotic resistance. The main way of fighting against IPD is using vaccines. The current vaccines are effective against 13 different serotypes out of the 100 different possibilities. The vaccines are very, very expensive to produce, and the current CDC list price is about $600 per patient. Because these vaccines are so expensive, there are programs such as the Global Alliance for Vaccines and Immunizations that subsidize the vaccines to provide easier access to developing countries. Despite these programs, there are still 55% of the global infant population that are not vaccinated. The efficacy of the vaccines against IPD depend on many different factors, such as the genomics of the bacterial population and the age structure of the human population. Introducing a vaccine can have unintended consequences, since the non-vaccinated strains will replace the vaccinated strains in the bacterial population. The replacing strains can be more invasive or resistant to antibiotics, and there are a few cases of this happening that are documented. For example, in the UK, after the pneumococcal vaccines were introduced, there was a 4% increase in adult IPD. There was also an increase in penicillin-resistant meningitis in France. As I mentioned previously, the vaccines are very expensive to produce. The main factor affecting the price of the vaccines is the number of different serotypes the vaccine targets. If we were better able to predict the population dynamics of the bacteria after we introduce the vaccine, we would be able to produce more effective vaccines for cheaper. Understanding the population dynamics of bacteria is crucial for developing better vaccines. Based on observations about bacteria populations before and after introducing a vaccine, researchers have developed a mathematical model that describes this behavior. This model is based on the relative frequencies of the so-called accessory genes in the bacteria. As the different bacteria strains are competing against each other, if a particular genotype gets too common, it will negatively affect the fitness of the bacteria. These different selective pressures result in an equilibrium distribution for the frequency of the accessory genes. This equilibrium distribution can be used to formulate a deterministic model for the population dynamics as a system of differential equations. Now that we have a mathematical model for the behavior of the bacterial population once we introduce a hypothetical vaccine, we can use it to optimize the vaccines against certain criteria. We are primarily interested in reducing the amount of invasive pneumococcal disease. So invasiveness is the main criteria that we want to reduce in the resulting bacterial population. Other important criteria include the antibiotic resistance of the surviving strains, as well as the cost of the vaccine. The problem is choosing the optimal subset of serotypes to include in the vaccine out of the 100 different possibilities. This results in a large combinatorial space of different vaccine designs. For example, in one particular case of a refugee camp in Thailand, there was over 100 trillion different possible vaccine designs. Evaluating a possible vaccine candidate requires solving a large system of differential equations. The end result is that we have a constrained combinatorial optimization problem over a computationally intensive function. Bayesian optimization is one approach to optimizing expensive black box functions. It was applied to this particular problem in a paper last year, and they were able to almost halve the IBD in the adult population in the computational model. My work on this problem has been re-implementing the original MATLAB code in Julia. The re-implementation of the code in Julia improved the performance by an order of magnitude. This improved code can be used to model larger bacterial populations as well as different bacteria such as E. coli. Instead of using a continuous version of Bayesian optimization, which is not ideally suited for this problem, I've also explored the use of discrete Bayesian optimization, as well as explored the use of automatic differentiation of the differential equation solution to come up with better ways to optimize the vaccines.